some reminders. You should have finished homework 20. If you didn't, you should get on that. I will be posting homework 21, which will be the last homework assignment. It will be due on Thursday. We have a quiz on Wednesday. I'm going to have that be done on Canvas. And we will do, I will open the window for you to take it in the morning. I will close it at midnight, so you'll have that time frame. That doesn't mean you get 24 hours to take the test. That means that once you open it, you'll have about a half an hour to take it. There is on Canvas a practice quiz that covers a lot of the material. You can look at that. After Friday, we have one class day. I will use that to return your exams and wrap up any loose ends that we have. Final exams, and a lot of you are freshmen. You can find this by going to the registrar's webpage. If you go to the portal and then departments, look for the registrar and you'll find this. And so this will give you the exam schedule. It can be a little bit confusing to read. So it is, this class is 11 a.m. on Monday, Wednesday, Friday. So you find your class and the day is to the left. So our exam is on Monday, December 12th. And our time is at 12. Okay. I will allow you to take your test with one of my other classes. So I have a class at 10 a.m. That exam is on the 9th, the Friday before. So if you are trying to get all of your tests done so you can get out of here, you can do that. I need to know ahead of time, so I'll ask you on Wednesday. And that exam is at 9 a.m. Okay, so it's not the time of the class. You have to look at the chart to see when it is. I also have this written at the back of your syllabus, but if you want to compare different classes, this is what you can look at. And then Monday, or my 1 p.m. class is going to be also on Monday, December 12th, but later in the day. So those two, same day on those, okay? And then you'll notice it says reading day. Basically, there's kind of a blacked out day so that your professors aren't trying to shove more information into your head the day before you're taking an exam. So you have one day to reorganize those thoughts, and what most people do is sleep. That's a good thing too. I think it's important. Okay, questions about this? We last week or week before Thanksgiving talked about how light was a wave, and then we talked about some properties of light, wavelength, the frequency, and the energy. Using your thumb, if the wavelength goes up, what happens to the frequency of a wave? Yeah, I'm seeing lots of thumbs down. That is correct. Okay, so if we look at C equals lambda nu, and I'm going to move this over. If we look at C equals lambda nu here, then if one, this is a constant, so if one of these goes up, the other one has to go down to keep them constant. All right. If frequency goes up, what happens to the energy? Couple of votes look correct. Okay, so since these are on opposite sides of the equal sign, if this goes up, this also has to go up. So they do the same thing. Okay, so these might be similar to questions I might ask you on a quiz or a test. Okay, so good idea to know those. Now, this one's going to cross these two equations. If the energy goes up, what happens to the wavelength? Yeah, the wavelength's going to go down. So this is a long wavelength, but low energy. This is a short wavelength, but very high energy. Okay. All right, so we said light was a wave, but we found some effects, black body radiation and the photoelectric effect that could best be explained if we assume light comes in little individual packets. We call those little packets of energy, anybody remember? Photons. All right, so photons at the airport getting on the plane says, all right, I'm ready to go. And they say, do you have any luggage to check? And he says, no, I'm traveling light. All right, so we got the photons. And then we said, okay, but we also have this idea of atomic spectra. Let me look at this one here, where different elements have different lines of color that show, and that can best be explained if we have electrons behaving as waves. So light is a wave that can behave like a particle. Electrons are particles that can behave like a wave. That's what we mean by wave-particle duality. And you have both of those at the same time. All right, we also said that the difference between the first two energy levels is really, really big, okay? So when I have this circle here, I'm showing that by, this is the first energy level, this is the second energy level. That distance is big. That's to illustrate that the energy difference is big. The next energy difference is smaller, and then the next one is smaller, and the next one is smaller. We also said we're not going to use circles because that just takes up too much room. So we're going to use lines. So we show that by going vertically. The big difference here, smaller difference, and then smaller, smaller, and smaller. All right. All right. Does anybody still need this? Okay. So one of the points was that each element has a distinct set of lines. So we gave the example that sodium has these bright yellow lines, and that's why a sodium lamp, like the lights out on Giddings Circle, wherever Giddings is, they have kind of a yellowish glow. Other street lamps might have a purplish glow. They usually have mercury vapor instead of sodium. Okay, so different elements give different line spectra. All right, so we are going to be talking about the Bohr model. And remember, it's a model, so we know it has problems, but it helps us simplify things to understand some of the orbital stuff we're going to be dealing with, okay? We are going to be talking about the ground state. Most of the time, that's what we are referring to. So the ground state is when all the electrons are in the lowest possible energy levels. So they're settled down for the night, ready to be calm. If we pull the electrons away, as we did when we had the lamps that were exciting them to give off light, that would be an excited state. Okay? But we're going to be focusing on the ground state. Are we good here? Okay, there's nothing to write down on this slide. I just wanted to point out that this equation is going to show up in your book. This is how we calculate all the stuff that we're talking about. So there's lots of math that goes into this. And so we know these things based on one proton and one electron, a hydrogen atom, and we can tell pretty definitively all of the stuff that I'm about to say for hydrogen, okay? And this equation is kind of the start of how we would establish that. All right. The other thing that I wanted to point out is that we can see the visible light for hydrogen. We can see these colors, but we can't see the ultraviolet. That's also coming out of that lamp when we're looking at that. We also have infrared coming in. So that light is also coming up. We can't see those. And that's going to be true whatever we look at. There's going to be light in various parts of the spectrum. For hydrogen and helium, the one that's the highest energy is usually ultraviolet light. By the time you get into the transition metals, that area is X-rays. So it gets higher and higher energy. And then by the time you get into, say, the lanthanides, the really heavier elements, even this second area is X-rays. Okay, so there's a whole bunch of X-rays. So you have different energy levels for the different ones. Now, before we go on, I want to remind ourselves about the different kinds of electromagnetic radiation. So we just talked about visible. We talked about ultraviolet. What other kinds are there? I mentioned two others. Infrared, ultraviolet. Was the really high one I said? Yeah. So gamma is a really high one, but there were X-rays that we talked about, okay? Gamma rays and X-rays, and there are two more, low energy. Microwaves and radio. Okay, which of those seven, and I'll tell you visible light is right smack dab in the middle, which of those seven is the lowest energy? Microwaves is second lowest, so that's a good guess. Radio is the lowest, okay? All right, so questions I might ask you on a test or quiz might be to put these things in order of their energy. So this might be something to take, 20 minutes, try and remember the order and see if you can write them down. All right, so if visible's right in the middle, then the next one is right next to visible. So it's going to have a color in its name. So what's the next one going to be? Infrared. So infrared means lower. It's lower energy. Infra means lower. I'm going to call that low-ish. And then visible light is in the middle. And then there's another color one that's going to be next. What's going to be the next one? UV. So this is high-ish. And which one's next? X-rays. And that's kind of the highest one we normally deal with. And then the highest one overall is gamma. What's that?
I said we don't want to deal with it.
No, that's how you get an Incredible Hulk. So you don't want to do that. So we said that we get this Bohr model by looking at the hydrogen atom. And the hydrogen atom only has one electron, and it works really well. Now, since all of the protons in the nucleus are kind of stuck together, this also works if I have helium +1 or lithium +2 that only have one electron. It doesn't work so well if I have more, because the electrons start pushing against each other. They want to get away from each other, but they want to get close to the nucleus, and that causes all kinds of things. So it doesn't work well for polyatomic atoms or electronic atoms. So the way that physicists or chemists count is 1, 2, many. Once you get to 3, then it's just so complicated, the math is just horrendous. So if you take this class next semester, you're going to be working on chemistry 112. You're going to be doing computational chemistry. Computational chemistry is using computers to do all the calculations that are really just too much for us to handle with multiple electrons. And so that looks at, well, if we make some assumptions, can we kind of guess what's going to happen with a carbon or with a silicon? And once you get past the third row, they have a really hard time dealing with all of those electrons. Okay, so it really is hard to do. So this is kind of the disclaimer that says, we know what we're saying is true for hydrogen. We are going to assume that it is true for other elements, only scaled to the number of electrons and the number of protons that those have. All right. And I think I'm skipping this one. Okay. So what we're going to talk about now is orbitals and how we can describe those orbitals. And then at the end of class, we'll get to electron configurations. So I like to think of orbitals as homes for electrons. Now, orbitals are not a physical thing. So if you think about an airplane flying, if you're an air traffic controller, you might talk about the channel that that airplane is on, or the path that it is, or the ceiling of the sky. Now, there aren't physical objects there. It's just describing a location. And that's kind of how orbitals are. So it's the location of our atoms. Now, we can describe them with different numbers. And the first number we're going to use is the N, which is the energy level. We've already talked about that, how close it is to the nucleus. So at our first energy level, we have one orbital. And each orbital can hold 2 electrons. So at our first energy level, we can have 2 electrons. In our second energy level, we can have 4 orbitals. And since each of those 4 can hold 2 electrons, we can have 8 electrons. Now, the shape of an electron, or sorry, the shape of an orbital is not really a physical shape. It's really a shape of the area where the electron might be. So most of the time we think of that as being a sphere, that it can kind of be anywhere in this sort of spherical space. But it turns out for some electrons that shape is a little bit different. So we are going to have a description of sublevels. The S sublevel is going to be a sphere. And so we are going to pair the sublevel with the principal quantum. I have this one, it's very small. This would be an S orbital, but I might say this is the 1s because it is the smallest. Then I might have a 2s, which is a little bit bigger. Then I might have a 3s, same shape, but a little bit bigger. And then I might have a 4s, same shape, but a little bit bigger. And then I might have a 5 or a 6 or 7s. Okay, so the only difference between the numbers is just how big they are. Okay, so the number part of our description is the N, the principal quantum number. That tells the energy level, but it also tells how big it is or how far away from the nucleus it can get. A p orbital is going to have 2 lobes, and it's going to look kind of like an infinity sign, like this. Okay. And we're going to talk in a minute about how it can have an orientation. It can be shaped like, or pointed like this, but with the same shape, it could also be up and down, or it could be in and out. Okay, so it can point different ways. Okay. So, the S is a sphere. The P kind of has a dumbbell shape. Now, the P orbital also has an area where it can't be. That's why it has this shape. It can be above this line. It can be below this line, but it can't be on this line. Okay. This line is called a node. Okay. Now, if I have an orbital that is in a sideways orientation, I still have a node, but the node is pointing in a different direction. Okay. So an S orbital doesn't have any nodes, right? It can be anywhere. A p orbital has 1 node. A d orbital kind of looks like a 4-leaf clover. This might be our d orbital. There we go. And it has two nodes, across and up and down. And then each of these can also point in different directions. So I can have it like this. I can have it laying flat. I can also have it coming in and out. So there's lots of different directions I can. Okay, so we're going to think of the orbitals as being like apartments. Since they're the homes where the electrons live, it's going to be an apartment that can hold 2 electrons. There are 2 beds in this apartment. And if we have lots of different orbitals, it's kind of like having an apartment building. Okay, and the apartment building is going to have different floors on it. The first floor always only has one apartment. Maybe that's where the superintendent lives. Okay, you got the super and his wife, or super and her husband, or whatever the case may be. Super and their dog. They're living in this apartment. The next floor up, we have the s orbitals, but we also have p orbitals. And notice there are 3 of these. Okay. So this is like having different hallways. So I've got the hallway right above the super's apartment, and then I have the hallway where I've got some different kinds of orbitals. And these happen to have that shape of the infinity sign or the dumbbell. If I go to the next floor up, I can add one more hallway, and that hallway is going to have these 4 leaf closures. Okay. We're going to come back to this drawing, but if I'm looking at hydrogen, I would represent the electron of hydrogen by an arrow. And we'll talk later about why it's going to be an arrow, but for now, just remember an arrow means an electron. Each of these lines is 1 orbital. So this is 3 orbitals, this is 5 orbitals, and this arrow here is 1 electron. So in the ground state, the electron is going to go to the lowest possible energy. It's going to go to the lowest orbital. All right, so this is kind of showing a distribution or probability of finding the electron. So think of it this way. If I were to take 1,000 pictures of where the electron was, instantaneous snapshot, and place them all on top of each other, it might look like this. These are all the places I found that electron. So I was more likely to find it close to the nucleus, but I could also find it farther from the nucleus. Now, if I were to do this for 1,000,000 or 1,000,000,000 or a quadrillion times, every once in a while I might have the electron here or way out here. So there's really no edge to the orbital. There's no stopping point. So this is kind of showing like it has an edge, but it doesn't really have an edge. This is where you're 99% likely to find the electron. We might find a stray one outside of this, but this is where you're most likely to find it. This graph is called a probability distribution. So probability is how likely you are to find it. So where it's very high is close to the nucleus, and that's where the dots are very close together. And it's less likely farther away. Okay, so that's for an s orbital. If we were to do this for a p orbital, we would find a blob on top and a blob on the bottom, and then nothing in the middle. All right. So each orbital has 2 electrons. The orbitals can be described with 3 quantum numbers. Okay, so our quantum numbers are n, which we've already described. That's the energy level. L and m sub l. So L tells us the shape or the subshell that it's in. And we can think of that as being like a different hallway on the atom. So the S and the L are both on the same level, but they're on different hallways. And different hallways have different shaped apartments. So this is what a P orbital or a p apartment for an electron might look like, this is what a d orbital might look like. And these gray diamonds are showing the nodes. So there's one node here, cutting that in half, and there's two nodes here. Okay, so the L is also showing the number of nodes. All right, so M sub L is just our way of putting a number on the door to tell the difference between one apartment and another in the same hallway. Okay, you might have apartment 3D or apartment 141. In the orbitals, it's going to be the numbers 1, -1, 0, depending on what the M sub L is. All right, anybody still need this slide? Okay. So of these three, the two most important are the N and the L. All right. So I said they were quantum numbers. N we've already been using as a number, so that's not surprising. Sometimes I will call it the principal quantum number. I might also refer to it as the shell, the energy level, or describing the size, okay? So if I say which energy level is this on a quiz, you're going to be looking for what is the number that goes with N, all right? Or if I say, what does N represent, and you've got different names, then you're going to be looking for principal quantum number, or the shell, or the energy level, or the size. Now, when we get to electron configurations, we're going to use the periodic table to help us write those out. And what we're going to find is that for any given element, the row that it's on the periodic table, whether it's the first row with hydrogen and helium or down at the 7th row near the bottom, that number is going to correspond to the last orbitals that are being filled. Okay, so we will come back to that idea, but just kind of keep in mind that that N can tell us about the periodic table. Okay, the second one, L, is the angular momentum. It has another name that I like, azimuthal, but you don't need to know that one. So if you've had physics, you know that momentum tells us about how fast we're going, but also our weight. So it combines those two things together. Angular momentum talks about that as you're curving around something or going around in a circle. So if you've been in a car and you've turned very sharply while you were going fast, you've kind of felt that angular momentum. That shifting of your weight is tied to your angular momentum. That the car wants you to change your angular momentum. You want to keep on the same angular momentum. So we're not going to go into calculations for angular momentum, but that's where that term comes from, because the electrons aren't just going in a straight line, they're moving around, okay? So L, we call the angular momentum. Sometimes we will call it the subshell, and it describes the shape of the orbital. We describe the shapes as spherical, dumbbell shaped, or infinity, four-leaf clover shaped. The d orbitals also have another shape that we'll get to in a minute. Now we call these quantum numbers. Each of these numbers corresponds to one of the letters. Okay? Yeah, Sean.
So I know you said the shape is like where you're most likely to find it, but where it's angular momentum, is that also due to like the way that they're trying to curve in their path?
All right, so we talk about an S orbital, and we will almost always use the letters because otherwise we just have numbers all over the place. But the letters also correspond to a number. And so S corresponds to 0, and that just tells us I have 0 nodes. And the L corresponds to a P, I'm sorry, the 1 corresponds to a P, and that has 1 node. And the 2 corresponds to the D, and the D's have 2 nodes. All right. And there's a little more math involved with it too, but for our purposes, remembering that it corresponds to nodes is probably the most helpful thing. Now, we also have some rules associated with which numbers are allowed when. But first, let's look at M sub L. So M sub L is the magnetic quantum number. So remember, these were electromagnetic radiation. Okay, so it was a changing electric field and magnetic field. So electricity and magnetism go hand in hand. They are like Siamese twins, always together. So when we got an electron moving, we've got electricity, but you've also got magnetism. Okay, so M sub L is telling us a little bit about that magnetism. Now, we're not going to go into that in this class. If you want to get into that, take PChem or physics or something. But that's where that number comes from, is that there's magnetism associated with it. And what that's going to do is that's going to tell us which way the orbital is pointing. Now, for our purposes, we're not going to specify the vertical one is 0 and the left to right one is 1. We're just going to know that we have different numbers, and that's because we have different orientations. So you don't need to know which orientation is which. All right, anybody still need this? All right, so I said there will be rules. So our first rule is that n is a positive number because it's telling us which energy level. So you can't have the negative 1th level. So it's going to be 1, 2, 3, 4. L is going to be a whole number, which means it can include 0, but it has to be less than n, and it can't be negative. So in our first energy level, the only thing less than n, but not negative, is 0. Okay, so for our first energy level, the only thing we can have is L equal to 0. And L equal to 0 was the sphere. So we just have one orbital there. In our second energy level, we could have 0, that's less than 2, but we could also have 1. In our third energy level, we could have L be equal to 0, L be equal to 1, or L equal to 2. But remember that each of those numbers actually corresponds to the letter or the shape. We got 3 different ways to identify these things, which is confusing, I understand. But that means we can have an S, a P, or a D. We can have a sphere, a dumbbell, or a clover. And then the rule for M sub L is that it goes from the positive of L to the negative L and all the integers in between. So basically that says the magnitude or absolute value of M sub L can either be the same thing as L or less than L. So all of this quantum number stuff is all about patterns. So for an S orbital with 0 nodes, M sub L can be equal to L, which is 0. And the opposite, or negative of L, that's still 0. And everything in between. So it can only be 0, right? For P was the same thing as 1. It can be positive 1. It can be negative 1. And everything in between, so it's 0. Okay, so we've got this pattern here developing. So for D is equal to 2, so we can have +2, -2, and all the integers in between. So see how we're kind of forming a triangle or Christmas tree here, right? I have 1 orbital, 3 orbitals, 5 orbitals. Now my next set, which is going to be F, my next set, how many orbitals do you think it'll be? 7. We're just following the pattern. And where do those numbers come from? It comes from the possible values of M sub F. Because every time I add 1 integer on one side, I'm adding the negative as well. So I'm adding 2 more possibilities at each level. And so that's why it goes up by 2 each time. All right, so if L is equal to 1, which would be a p orbital, it can be +1, 0, or negative. This is just a chart that summarizes what we just talked about. I'm not going to spend time on this, but it's on Canvas, so you can take a look at it if it is helpful to you. And so on here, I tried to illustrate from that same diagram of the hydrogen atom, which we've been referring to as kind of like an apartment building, all the different floors, and then on the top floor, I've got the numbering system here for each of these. So those numbers correspond to the magnetic quantum number. We're not going to worry too much about what those numbers are. Just know that they exist. What we're more concerned about is underneath each of those, we've got a number and a letter. And so we're going to describe an orbital as a 3p orbital or 1s orbital. Okay, so that's going to tell us about the shape and it's going to tell us about the size. Now there are rules for putting electrons in. And the first rule is the Aufbau principle, which is also called the building up principle, which means you start at the bottom and you build up. So we can think of the electrons as following gravity. They trickle down to the lowest possible energy level. So hydrogen only has 1 electron. It's going to trickle down to the lowest possible orbital that it can go into, which is the 1s orbital. Oops. Thought there was more in there. Now, there are 2 other rules we're going to look at on Wednesday. We won't get to them today, but one of them is the Pauli exclusion principle, which is going to be applied on this next slide, but we're not going to talk about it. All right, so here's the hydrogen atom with its 1 electron. Helium then has 2 electrons. Can I put a second electron in that first orbital? How many electrons can go into an orbital? 2, so we can still put an electron in there. And so notice it's an arrow, but it's pointed down, okay? So the Pauli exclusion principle says in each orbital, you can have 1 that's up and 1 that's down. So what does that mean? That has to do with the spin of the electron. So the electrons can spin clockwise or counterclockwise, but rather than trying to show that with a curved line, we just show it with an arrow, up or down, okay? So we have our 2 electrons in there. And so helium is going to have 2 electrons in the lowest possible orbital. Now, when we get to lithium, it's got a 3rd electron. That story is going to change. But let's look at hydrogen and helium first. Writing electron configurations. An electron configuration shows us which orbitals are being used and how many electrons are in it. It's listing all the filled orbitals. And it starts from the bottom and builds up. So for each kind of orbital, we're going to list N, L, and how many electrons are in there. So on this one, I've got D that's still showing down here. We're not going to worry about which of these spots they're in. We're just going to say collectively in all of these, how many electrons are there. Okay? So the way that would work for hydrogen, it's one electron. It's in the lowest possible orbital. It's the 1s orbital. So we would say 1s, and then we would put a 1. Now notice that's a superscript 1. It's smaller and it's up high. That's important because once we have a lot of electrons, we're going to squish all this stuff together. So if you don't make it smaller and up high, that number is going to get mixed up with the other numbers. Then for helium, there were 2 electrons, but they were both in the same orbital. So its electron configuration would be 1s with a little 2. Okay. Now, if we look at lithium, we had our 2 electrons for hydrogen and helium. Lithium has a 3rd electron. Can that 3rd electron fit in the bottom orbital? No, because it tops out at 2 possible electrons. So it's going to go into the next orbital. And the next orbital is in layer 2. And you might be wondering, well, how does it decide between 2s and 2p? It turns out that once you get multiple electrons, instead of all of the level 2 being at the same place, there's just like a little energy difference, okay? So the s's are always going to be a little bit lower than the p's. And that's how we'll build it. Okay, so the electron configuration for lithium would be 1s2, because there's 2 electrons in there, 2s1. Look like that. Okay. And so what we would notice if we did a bunch of these is that every time we have an alkali metal, it's going to end in S superscript 1. So sodium would be 3s1 at the end. And cesium would be 6s1 at the end. Okay. If I did the alkaline earth metals, the next column over, they're going to end in S2. So beryllium would end in 2s2, magnesium in 3s2, so on and so forth. So these electron configurations tell us about the organization of the periodic table, or the periodic table can tell us about the electron configurations. So I know this is too small to see, but if you download the slides, you will be able to pull this up and look at it. And what you'll see is at the bottom of each of these is the very last part of the electron configuration, and it's the same for the whole column except for the energy level. So it'll be 4s2, 4p4, or 5s2, 5p4, so on and so forth. Okay, we'll look more at electron configurations on Wednesday. Okay, so what I want to do is just kind of practice a little bit with looking at orbitals and describing them. Okay, so when I see a shape like this, I know that this is an orbital, and it can be described by 3 quantum numbers. Now, 2 of them, well, 1 of them I can tell just by looking at it, and that's the shape. So the shape, I can either give a number or a letter. So which number or letter goes with this one? It is number 1. What letter goes with number 1? P. So this is a p orbital. It also can be described by its size. You can't tell that without having relative sizes. So, but I might say this is a 2, energy 2. And I might say that its orientation is 0. Okay. Now those you can't tell just by looking at it, but it has those numbers. Okay, so when I look at this, I can tell that it has L is equal to 1 or P, and it is one of 3 different kinds of P orbitals. Okay, so every set of P orbitals, there are 3 of them. Every set of D orbitals, there are 5. So if I look at this, this is all 3 kinds of p orbitals at the same time. So I've got the one that I showed first, up and down one, and then there's one going this way and one going this way. That's a lot to digest visually, so we hardly ever show them all at once. All right, so if I look at this, it also can be described by its size or energy, its shape, and its orientation. What can we tell by looking at it? L is equal to 2, okay? So the four-leaf clover has a node going this way, a node going this way, and this is a d orbital. D and 2 mean the same thing for L. Okay, so this can be described by its energy level. Now, its energy level has to be at least 3. That was one of our rules, is that the energy level can only hold orbitals that have the L less than it. Okay, so energy level 2 can't hold an L equal to 2. This is an L equal to 2. So it has to be at least 3. And it has a shape. And then we might describe its M sub L. Again, you won't know which one it is, but it has one. Okay, so when you see this, you should be able to determine that this is 2 or D, and it is one of 5 orbitals, one of 5 D orbitals. You should also know how many electrons can fit in. How many electrons can fit in this one orbital? How many electrons can fit in any one orbital? 2. So just like the sphere, this can only hold 2 electrons. It looks more complicated, but it still can only hold 2 electrons. All right. So that is all I have for today. Again, on Wednesday, I will pass back your test. Your quiz will be open that you can take it. If you want to do it before class, that's fine. And we will finish up with the electron configurations.